When we shift from classical to quantum mechanics, we trade the sharp geometric ellipses of planetary orbits for the smeared probabilities of standing wave clouds. In 1916, 12 years before the arrival of modern wave mechanics, Arnold Sommerfeld attempted to extend the Bohr model by applying relativity to these classical elliptical paths. He arrived at a formula for the fine structure energy levels of hydrogen that was a perfect match for the experimental data. Sommerfeld had produced this result over a decade before Paul Dirac established the exact relativistic quantum mechanical solution in 1928. Werner Heisenberg later looked at this chronological gap and described the accuracy of the earlier formula as a miracle. Physicist Erwin Schrödinger was more skeptical, calling the alignment a fortuitous coincidence. Both interpretations overlook a deeper mathematical reality. This alignment arises from the specific architecture of Coulomb symmetries, which forces the classical and quantum results into the same functional form. To see how these eras reach the same conclusion, we place the models side by side. On the left is Sommerfeld's 1916 fine structure equation from classical integrals. On the right, Dirac's 1928 solution. Despite the 12-year gap, the formulas are structurally identical. We can explain this convergence by applying a semiclassical approximation to the Dirac equation, a process that reveals exactly where the two models overlap. This comparison shows how pre-spin classical mechanics was already probing the underlying structure of relativistic spinor wave mechanics. The process begins with the stationary Schrödinger equation, which must be separated into spherical coordinates to account for the central field of the atom. This gives us the radial wave equation, u double prime plus q of x times u equals 0. Semi-classical approximations usually fail at the origin, the very center of the atom, where r equals 0. We correct for this using the Langer transformation, substituting the coordinate x with e to the power of z. This transformation alters the equation's behavior near the center, generating a specific shift term, -1 over 4x squared. When we incorporate this shift into the q function, it defines the effective momentum for the electron. This transformed effective momentum allows us to apply semiclassical quantization to any central Coulomb problem. Applying our quantization rules to this momentum yields a generic integral containing 3 parameters, a, b, and c. Evaluating this integral is a technically demanding process. Sommerfeld solved it by defining a contour loop across the 2 sheets of a Riemann surface. The result is a simple algebraic condition, b over 2 times the square root of a minus the square root of c equals the quantum number nr plus 1/2. We can reach this same result independently through parameter differentiation, confirming the consistency of the solution. This means that any wave equation we can map to these a, b, and c parameters will result in the same analytical solution. Records show that Schrödinger actually solved a relativistic wave equation before developing the non-relativistic version we use today. His 1925 Winter Notebook contains the draft for this relativistic attempt. When we map his math to our parameters, we find a and b as expected, but parameter c is determined entirely by orbital angular momentum, L. Without including electron spin, this parameter produces a fine structure split 8/3 larger than what we observe in nature. Schrödinger recognized this mismatch when comparing his results to high-resolution spectroscopy. Because the math disagreed with the physical data, Schrödinger discarded his relativistic draft and published only his non-relativistic work. In 1928, the Dirac equation provided a new starting point by treating the electron as a spinor. Applying the Langer transformation to the Dirac radial equations yields a revised effective momentum. Comparing these Dirac parameters to Schrödinger's earlier draft shows us exactly what changed. While a and b remain the same, Dirac's parameter c is now defined by total angular momentum, j. By accounting for total angular momentum, Dirac's model mathematically incorporates the spin correction that was missing in 1925. We can now place these Dirac parameters back into our generic algebraic solution. Substituting Dirac's specific a, b, and c into our master key formula begins a process of algebraic reduction. We simplify the expression to isolate the energy, epsilon. This simplification results in the exact formula Sommerfeld reached in 1916. The path is now clear. Dirac's relativistic model, when viewed through a semiclassical approximation, collapses into Sommerfeld's historical result. These heuristic predictions from the early 1900s are a direct mathematical output of the WKB approximation applied to modern spinor mechanics. This mathematical convergence holds across three different frameworks: classical action integrals, semiclassical approximations, and modern exact solutions. Each of these approaches relies on the same underlying algebraic structure to define energy levels. This happens because the spherical symmetries of the Coulomb potential create a mathematical bottleneck, restricting the form that any analytical solution can take. Sommerfeld reached the correct result because the internal logic of the potential allows for only one consistent functional relationship between energy and momentum. The 1916 guess was a reflection of the geometric constraints built into the universe itself.